Okay, so let's have a little think about this, some circuits, and let's just build one. Let's stick in a battery and stick in a bulb. And let's think about what it is that's going on in here. Okay, so let's think first about some wires in. And there. Oop, get that out there. And then let's put it in here. Let's put a switch in. Let's go here. And here we go. Close the switch. And here we go. It's moving. Yay! This is what we want to happen. So let's think about, what's going on in this circuit. What we saw last time is that we have this flow of current, okay, which is this current, which is the flow of charge. Now the convention would be positive to negative, so it would go that way around. But if we're actually worried about the flow of the actual particles, well, in a circuit, it's electrons. That occasionally is important when we start thinking about the interaction of things with current flow. Now, what we can do is that obviously we can just the circuit for a moment. We can measure the current flow with an ammeter, and what this allows us to do is to link that directly to, if we were to measure the width of this thing, and we can work out I equals NAVQ, we'd be able to work out this. And we're going to do that when we're back in the labs to actually have a bit of chance to play with this properly. So we will do that. But let's instead focus for a little moment before we come back to the current. We'll come back to it in a moment. Let's think about the voltmeter, what the voltmeter measures. Okay, and we can stick the voltmeter, and you might remember that it's this weird sort of thing. You stick a round component, and it gives you a number. And you hopefully might remember that this number up here, when you measure your voltage around a battery, is the same as the voltage you'll measure around the component. 9 volts, 9 volts. And let's get our second voltmeter out. Do that same here, and measure that here. Now the important thing is that the circuit works irrespective of whether we've got a voltmeter in there or not. That's the important thing to remember. But how do we tell the difference? What is the difference between this reading that's up here, going on up here, and this reading that's going on down here? Well, the question that we have to answer there is whether we are doing stuff to the charges. So whether we're, as things go through batteries, they are given energy, or whether it's the components themselves that are doing, releasing energy. Is the work being done on the charges, as it happens up here, or is the work being done by the charges, which is what's going on during the bulb? Now, what we often do is if you take your voltmeter and you stick your stuff around there, you'll measure 0 between 2 wires, because in this simulation, wire resistivity, we're always assuming that wires have 0 resistance. Now we can give them some resistance. See what happens. So we can actually see that there will be some, change in the voltage, change potentially, but we're going to always assume that our wires have no resistance. We're going to assume that at the moment anyway. We'll deal with the real lab with what happens when we try and measure things. So how do we differentiate between this? Last in GCSE, we just used this blanket term, voltage. But now we're going to use two. We're going to use 2 bits of terminology. The first is what's going on up at the battery. Now this is, we're going to call this, rather than use the term voltage, we're going to use the term electromotive force, or EMF. Okay, and this is allowing us to define sort of work done doing to the charge page. At the bottom, we're going to call this potential difference. Now you might remember that in a circuit, there's sort of like there's an electrical potential. Okay, there's a potential for this thing for these charges to release a certain amount of energy as they travel around. Now, if we measure between 2 points on the wire over here, we get 0. Well, that tells us that there is no difference in the potential between here and here, because the charges haven't used any. They've not used any energy in traveling from there to there in our sort of ideal circumstance. The difference comes here around this thing, and it actually means that we can measure. We can stick this anywhere as long as we stick it on this side. We're always going to get 9 volts. So this difference, and it's why we need to measure the voltage in 2 places. We need to know what is the difference in energy before and afterwards. And so we're measuring the difference in electrical potential energy between charges that were here and charges that are here. Okay, so when we measure around a component, we're going to call it the potential difference. When we measure around a battery or a power supply, we're going to call it the electromotive force. And that allows us to work out whether stuff's being done to the charges or by the charges. So let's have a little definition of that. Okay. So in an electrical circuit, we need to differentiate between when work is being done to the charge carriers or by. Ooh, okay, hold on. So what this is about doing is, so we define sort of certain things. So we define this. So electromotive force, otherwise known as EMF, is the term used to describe when work is done on a charge carrier it has the symbol, so that silence, the weird curly E, and is measured in volts. And potential difference which some times people just call it PD, is the term used to describe when work is done by the charge carriers. And it has a symbol sometimes, sometimes PD, sometimes people just say V, okay, for potential difference, and is also measured in volts. Okay, so this leads to a sort of starting question, which is, okay, what's a volt? What is the defining nature of a volt? Okay, so, so 1 volt, which is named after Alessandro Volta, who's the guy who first invents the battery. Is the potential difference measured when 1 coulomb of charge, capital C, does 1 joule of work. So what that means is that as you're, if we think about something going through a bulb, okay, so we've got a bulb, and we were measuring potential difference around it with a voltmeter of 1 volt. That means that if I'm going to draw, like, there's a coulomb of charge, okay, for every coulomb that travels through, it's going to lose, from the moment it hits this junction to going through, it is going to pass on 1 joule of, it's going to do 1 joule of work in that component. So that is essentially, you're measuring the energy sort of lost or used, or the work done for each sort of big giant bag of electrons that may come in a coulomb. Okay, so so that's kind of, so as that coulomb sort of goes through, that's what that represents. Now, you might say, well, why don't we count in electrons and joules and so on and so forth? Well, it's because these numbers are going to be tiny, rather sort of like tiny. So we can actually say that, so what this is defined as being is that V is equal to W over Q. Okay, so that's our potential difference. That's the work done. And that's the charge. So another unit, so therefore another unit for voltage is just joules per coulomb. Okay, so another unit of potential difference is joules per coulomb. Okay, and that gives us sort of like, I think, so when you're measuring it, you're saying how many joules of energy are given by each coulomb of charge as they go through. If we consider, actually in 1 coulomb of charge, so we can actually consider the answer. So it's like, one coulomb is how many electrons? Well, it's 1 coulomb divided by 1.6 times 10 to the minus 19, which is charge on an individual electron, which is a huge number, 6250. So 1 over 1.6 to the minus 19 is 6.25 times 10 to the 18. So you can actually sit there and go like, oh, okay, here's, that's how many electrons are in a coulomb. So oddly, what that actually also means is for 1 volt, this is the amount of energy that they're actually holding on to. They're only holding on to 1.6 times 10 to the minus 19 joules of energy. So this is sort of where the definition of the electron volt comes from, because each coulomb, each thing is only holding this much energy. But even for an electron, that's quite a large amount of energy, because the mass of an electron is tiny. It's 9.11 times 10 to the minus 31 kilograms. So that's a lot of, it would be a, so therefore, so therefore in passing through a 1 volt battery, each electron gains 1.6 times 10 to the minus 19 joules. So that's the tiny number that we have there. So that is what we get when we get this. Now at the other end, our EMF, if we think about the same thing is going to happen, but if we go through a battery, we go through a 1, that's the idea. If we go through a 1 volt battery, got our coulomb of charge, same thing is going to happen in exactly the same way. Actually, negative positive is going to drag through that way. But as it goes through, the idea is if we stick a voltmeter around this, what we measure is a difference in how much work has been done to there, but if the work's done on the electrons, you end up with stuff that's having more energy on this side. So you end up still measuring 1 volt, so you get the same kind of idea. So EMF is similarly calculated as time equals over charge. In this case, it is the work that the battery is doing on those electrons as they travel around. So that's our thing. So, so this is our nice little like link between sort of the potential difference or the electromotive force that we measure in volts, the work that we're going to either be doing or doing by a battery or on a component in joules, and the charge that's flowing through. Now this means that what we can do is we can start thinking about as things flow through a component. So as charge flows through a component, the work done is work done, or therefore equal voltage times charge. And then as charge passed is equal to current times time, we've got Q equals I times T. This gives me to the equation you might remember from GCSE. We can put I times T into there, and we get the work done is equal to V times I times T. Now this is a much more useful equation than instinctively than this. Why in a circuit? Because current in a circuit is going to remain pretty constant, and the potential difference at various points should remain pretty constant. So time is just your only variable that's going to change a lot. But it also allows us to define power, as power is equal to work over time. This also leads to power equals voltage times current. So that's going to be another one of the equations you hopefully may remember from last doing it. They all really arise from these two sort of standard things. Charge is current times time, or current is really defined as charge over time, and work and voltage is defined as energy per unit charge. So so this is how we have these things. This is how these things are linked. So it gives us quite a few different weird kind of equations that we've got. So that's kind of what we have. So let's have a look back at this. Fantastic. Let's have a look at our circuit again and load up our circuit. So this is why it's been running the whole time, and none of this has changed. These haven't changed. We can throw our an ammeter in there to measure something, and go excellent. Measure that, and we can say, oh, okay, on there, that one, on that for a moment. We can sit there and say, oh, okay, current is going to be 0.9 amps, voltage is 9 volts. So we could say, okay, what is the energy usage, of this bulb over the course of, say, let's say an hour. So we could say, oh, okay, what's the usage in an hour? Well, we need our current, we need our voltage, we multiply by time, and we can work that one out. So there we go. So let's quickly, as a little example. So example, a bulb has a potential difference of 9 volts and a current of 0.9 amps. How much energy? Does it use in 1 hour? Well, we've got work done is equal to potential difference times current times the time. So we've got 9 times 0.9 times time, which is 3,600. So it's going to be 60 times 60. And there we go. 9 times 0.9 times 60. And we get 29,160 joules. And that is stuff we get. So it's some of the calculations that we can do. The key is just to remember there's this weird difference, So the only really new thing today is this new term, electronegative force and potential difference. So using those terms rather than saying the voltage. Voltage is going to be something that is a unit. Often when you were using the term voltage in the past, you were really talking about potential difference because we were only ever interested in the work done by, the work done by charges. But EMF is something that allows us to, calculate things when we deal with them in terms of, how long a battery might be able to run for. And we can see various things because it's quite nice because we can actually see that if you've got, a amount of energy that your voltage of your battery set up for, it allows us to then work out how much of a current it can drive for a certain amount of time. And there we go. That's what we've got today. Actually, it turns out, sorry, just unpaused it. I've changed my mind. We're going to do something else as well. We're going to do something else also to do with energy. And we're going to talk briefly, therefore, about particle accelerators. Our version is the electron gun. Now, as we saw last time with drift velocity, electrons don't really travel very fast in circuits, and the reason is that as they try and travel down a wire, there are the atoms that get in the way, the nuclei, and they sort of like bounce into things and sort of have this sort of weird sort of movement. But if you remove that, it actually turns out that with small voltages you can accelerate things fairly dramatically. And again, we'll see one of these sort of next time, but let's do the sort of theory. What we can do with one of these is we can build something to accelerate electrons through a vacuum. So what we can create is an electron gun made out of the following components. And this is the heart of old style TVs. If you've ever seen or wondered what the big giant TVs that we used to have to deal with look like, they basically are made out of this. And then we have a positive plate. So we have that connected. Supply. And we will have this connected. That's plus and that's minus. Right. Okay. So this is the principle of what happens here in an electron gun. Oh, yeah, that's annoying. So what will happen is we have a coil of wire. So the coil of wire, so coil of wire, which is number 1, the coil gets hot and emits electrons. Okay, so it's called thermionic. So therm, heat, ionic, turning into ions, emission. So what will then happen is, electrons sort of like pop into, let's draw them in blue, so we get some electrons that sort of pop out into sort of no man's land. Now what happens though is that they are negatively charged and we create a very, very highly charged positive plate. So this plate over here, which has a small hole in it, we're going to charge it up. Let's charge it up to plus 1,000 volts. So the potential difference between here and here is 1,000 volts. Okay. So what will happen is we've got 1,000 volts here, a kilovolt here. These electrons will move towards it because, of course, they will, because they are negatively charged. They like positive things, so they're going to move towards it. Now, many of them, they might hit the plate, but some of them, well, they're going to go through the hole. And if they go through the hole, then they will zoom off. And that is how you make an electron gun. You make sort of beams of electrons that fly through, and some of them will come out this way, and they are going to be traveling fast because there's nothing in here. This isn't like a wire where there's other stuff to collide with, and there's a drift velocity. These things are going to move quite rapidly. But let's work out how rapidly they're going to do. They're going to travel at 1 kilovolt. Okay, so as they move, so this end is called the cathode, and they move to the anode. So as the electrons are accelerated to the anode, work is done on them. So how much work? Well, the work done is equal to the charge times the voltage. The charge is the charge on an electron. So now we would leave that as we can actually leave that in a unit called the electron volts, because we just don't multiply through by the charge yet. But we're going to do that. So we have 1.6 times 10 to the minus 19 times 1,000 volts. So that's our charge times potential difference, I should have said. So we end up with there is 1.6 times 10 to the minus 16 joules. That is the amount of work done on each electron. So, and we said originally, over here, oh, it's a lot of energy for an electron. Well, they're in a wire, but if you're not in a wire, what can you do with that energy? Well, that energy, work, is converted to kinetic energy. Okay, so what that means is that that 1.6 times 10 to the minus 19 joules is going to equal the kinetic energy. Kinetic energy is half mv squared. Now, the mass of an electron is tiny. It's 9.11 times 10 to the minus 31 kilograms. So what this means is we can say, oh, okay, we do a bit of rearranging. Oh, I don't know why I put 10 to the minus 16. 19 10 to the minus 16. Okay, and so what we have, we can rearrange that to be that V is going to equal the square root of 2 times 1.6 times 10 to the minus 16 all over the mass, which is 9.11 times 10 to the minus 31. So that is 3 times 1.6 minus 16 over 9.11 minus 31. Big number, but we take the square root of that, and we get 1.87 times 10 to 7 meters per second. This, okay, is about 6% of the speed of light. This is how you build a particle accelerator for electrons. It's quite easy, actually. Now, this was at the heart, this idea, the electron guns at the heart of oscilloscopes, heart of televisions, lots of various bits of scientific equipment and things. Because essentially you fire electrons at things and you just have a target, whether it's a screen or something to fire at, and that may glow as the electrons strike things. It's also how you make X-rays. You start with an electron gun, you fire electrons into various metal surfaces and make X-rays via that. And so that is how we do that, because it's actually very easy to make a 1,000 kilovolt, 1,000 volt potential difference. That's not terribly difficult. the strongest one we've got in the lab will go up to about 5.5 kilovolts, unless, you know, in terms of inside there's an electron gun within a vacuum. But you can make these things very small, very easy, and it is quite simple to make them. So that's another use of this sort of difference. The potential difference, or the, you know, you could argue maybe the EMF between the 2 points is 1,000 volts, because that's kind of like representing the work we're doing on it. But that's another way of using the energy sort of equation. So we're going to do a bit of practice using them, and there we go.